Hello, Gina.
Hello, how are you?
Okay, how you doing?
Thank you.
Good, good. It's warm.
I'm also
You're animated.
I try to be.
Okay. Right. Well, it's unusually warm for October.
It is.
Wow.
I think we need to go pick apples.
Works for me. Yes, we have 3 handouts today.
So this is our last thing we're doing. So here we have a winner. They usually only have 2 events. I remember them talking about it, but we couldn't find that much.
We have 3 handouts on the front table. If you'll please grab them.
Bring this to the office. Oh, I know what you're doing today.
Today's Stereopsis Day.
I love this day.
For a flower. The story you told me last time, the guy who was scaring out flowers.
Is here. Sarah is here. Where's Sarah? Where's Alexa?
I called her before.
Gabby. Meg. Hi, Isabel. Hi. Isabel, we have 3 handouts today in the front of the room.
I always set an alarm for like 8:30, and then I wind up sleeping till 10 every time. And I'm like, no, it's 8:30. I'm still too tired for this. Seriously, I'm going to. was so excited. I was like, I wish it was like the was like increasing us. So I was like, oh my god, that was such great news. It takes so much to get. Do we get a class tomorrow? That's what my sister said. I don't either. Yeah, so I'm like, yeah, it's my sister's thing. She's like,
If you're just coming in, we have 3 handouts on the front table. If you'll please make sure you have one of each of the 3.
no, not forever. Yeah, it's temporary.
Got 3 handouts on the front table, please. Okay, we've got 12:30, so why don't we get started? Good afternoon, S&P. Welcome to the middle of week 9. A couple of ideas about where we're going over the next few sessions, just to set the stage for this. Of course, we've got the really good news. Right here we are on the 21st of October, and that means 1 week from today will be exam 3. Can we give it up for exam 3? Yeah. All right. So at this point in the semester, it's usually an alternation between exams and then papers, exams and then papers. So we're up to an exam 1 week from today. So we'll do this just like we've done before. We have a new slide that says about exam 3. And it looks very much like the other informative slides about exams, but just so we're all clear, the format will remain the same, mostly short answers and some graph drawing. You'll be studying the TED Ed questions, which are based on YouTube videos and the PowerPoints and the readings and so forth. So nothing particularly new there. We had an article to read or an abstract to read last time in the middle of the test, and we were asked to apply our knowledge to that. You might be asked to integrate some ideas from the writings that we've had. Recently we talked about partial blindness, and so that's one type of disability, and disability is a recurring theme in our power and justice course. So that's one possibility also for content on the exam. And the exam will be cumulative, but it will emphasize material since exam 2, which occurred on October 9th. Okay? So you've got that pattern down now. This will be the third of 4 exams. Okay, and I'll give you a couple of other reminders as we're getting close. Some other things, just to let you know about what's going on. We'll have some TED Ed questions for the Pulfric effect coming up on Friday. Those are already available to you. You can dial down to those. And then we'll also have a TED Ed for Monday's session where you're going to be reading an article that was published by some researchers at MIT who did some really interesting brain recordings in monkeys trying to understand the neural basis of visual attention while we're doing a visual search. And there are some people in the corresponding class who are actually conducting a visual search test, and this article will be particularly relevant to them, but I think relevant to all of us because visual attention is something that's pervasive in our everyday lives. So we'll get to understand a little bit about the neurophysiology of that, and then we're off to exam 3. So that will keep us busy for a while. All right? Okay. All right. So let me open up where we left off. You might recall we had some conversation about the connection between action and perception, and that was one of the themes in Jessica Witt's earlier paper. We had 2 similar papers. One was called See the Ball, Hit the Ball, and we had some conversation about that. And then we ended last session by taking a look at her in her S&P class, and we wanted to see how many connections we could make between her material, some of which was review for us, some of which was totally new, but lots of students had connections. So thank you all for that. I thought that was really well done, and I was inspired to see people connecting to the consciousness chapter. We hadn't talked about that in a while. That was nice to see. I also want to thank you for your responses on the metacognition survey. I hope that you find reflecting on your cognition to be really helpful. So that was how we wound up the last session. Okay, let's go ahead then and get into just a little bit of an overview on what was going on in the second article. Then we'll spend most of today talking about what you prepared for via TED-Ed, and that's monocular and binocular perception. So here we have putting to a bigger hole, golf performance relates to perceived size. Can somebody give us just the general theme in this paper, general ideas about what the investigators were researching? Okay, thanks, Claire.
It was very similar to the article about baseball, but they said they were using golf, and they were looking at the size of the hole that the golfers were putting into, and seeing whether or not those, again, like those who were doing well would see it as larger, and those who were seeing it small were doing poorly. But then in the second experiment, they went ahead and looked at whether or not that was a memory problem, whether or not they could remember how big the size of the hole was. So they made sure that they were able to see the hole in the second experiment, which was different.
Okay, really good. So this time around, they actually did have some experiments. That was one of the TED-Ed questions. But the theme was the same. The idea is, does your performance actually affect your perception? Right? And so we sometimes think about these as being different phenomena. There's the motor system, right? There's perceptual systems. Do they talk to each other? One of the themes you might have taken away from Dr. Witt's video presentation the other day was that, in fact, perception doesn't have to be a passive process. It can be very active. And what we're doing and how well we are doing might affect how we perceive things. So it's the case that we do have these baseball players, for example, who are seeing bigger baseballs, and here we have a continuation of that idea. Another variation, well, maybe some people have taken Dr. Heft's class on maybe environmental psychology, and you might have done some research projects on this. Anybody want to share if you had done something like that? Gabby?
Oh, yeah, we did this one where we asked participants to step over a gap.
Okay.
We put different variables in it, so one of the things was we got a big poster of like a chasm or like a cliff going into like a deep trench or something, and we would put that in between the gap.
Okay.
And we would see if they thought they could step over the distance, whether it was like just a carpet on the ground or the poster of the like big trench.
Okay, and we'll have some posters of big trenches in a moment. That's pretty cool. Okay, and so they actually didn't have to step; they were just reporting like how confident are you that you could step, or.
And the gap would change size, and they wouldn't actually take the step, but they would stand there and say if they could.
Yeah, all kinds of variations on this. Another variation is they have people stand at the bottom of our hill here at Denison, right? And you're looking up at that relatively steep hill, and half of the people are asked to wear a backpack that has almost no weight in it. The other half are asked to wear a very heavy backpack. So you've got this thing on, you come to the foot of the hill, you're asked to look up the hill and judge roughly how steep that is. And they have different ways of getting that report, like how steep is this? And when you're wearing a heavier backpack, people will report that the thing is steeper than when you're wearing a not-so-heavy backpack, right? So, and of course, the retinal information obviously is identical, right? And so the sensation presumably hasn't changed. At least the information on your retina has not changed. But how we're about to interact with that certainly does seem to have an effect on how we perceive it, right? So it's this J.J. Gibson idea of perception and action, right? So this is a recurring theme here. Okay, so basically the same kinds of ideas. I did just want to check in on a couple of other notions from TED-Ed. We had one question here where you were asked to think about this. And we see that here we're plotting course score as a function of perceived size. Okay, so you're putting to a hole of a particular size, and you're asked to report which you think is the most likely here. And the question, one of the questions was, how would this graph maybe look different if there were no association between these two variables, course size and perceived size? Or, excuse me, course score and perceived size. Okay, Meg, how would it look different?
The best fitting line would be flat and horizontal.
Yeah, right. So the best fitting line would just now have no slope to it whatsoever. That's a recurring theme in all of science, not just psychological science, is that typically you're plotting some variable here, and you have that maybe you're manipulating, or maybe you're interested in the effect that it has or the association it has with some variable to be predicted. Whenever that's really, really flat, you've got no effect. Right? So we can see that here in the scatter plot. There was a similar idea. I think I might have asked you to draw it on draw 2 here. We asked you, if there was no effect for easy versus hard, what might this look like? And several people responded well on that. These two would be of equal height. Right? There would be no change in our dependent variable, which is apparent size in centimeters, as a function of whether you were in the easy or hard condition. Right? And that was an experimental assignment, right? So people were assigned to be at either this distance or that distance, and it might have been something like 0.4 meters versus 2.15 meters, whatever those numbers were. Okay, you're at a longer distance or a shorter distance, and in principle, that didn't have to have an effect, but it actually did. And Claire mentioned some of the controls that they had for that in experiment 3, where they had you viewing the hole that you were going to put into from a fixed distance while you were making the judgment about how big that thing was, even though earlier you were assigned to either the easy or hard condition. Okay? So they were controlling for memory in that particular case. All right, so a nice set of experiments from Jessica Witt on this idea about how our actions might be influencing our perceptions. Okay, any questions on any of that? Okay, why don't we proceed then to our main event for the day. And we were viewing a video and doing a TED Ed lesson on depth perception. So we moved out of now form perception, and we're getting into really one of the last features that we're going to talk about. We'll talk about this today. We'll talk about it on Friday. On Monday, we'll do visual attention, and then on Wednesday, we have the exam, and then after that, we're going to be into auditory land. Okay, we'll be doing auditory phenomena. Okay, so let's talk a little bit about some of the main ideas here. First, I wonder if somebody can tell us maybe what the primary problem is, the primary challenge is in depth perception. Jess has something. Yes, nicely stated. And Sarah also had her hand up. Did you want to say anything more than that? Okay, same thing. But thank you, sir. And thank you, Jess. Yeah, that's exactly it. Right. So the world really is three-dimensional. We've got this dimension. We'll call it X. We've got this dimension. We'll call it Y. And we'll have the distance separating me from Jess. We'll call that the Z plane or the Z dimension. Right. But now, as all these photons are coming at us, those are landing on a relatively flat retina. It's extended this way and it's extended that way, but it's not extended this way. So we lose some information about the real world, and the challenge is how do we begin recovering that? The second question from TED Ed was conceptually similar. We asked about something called the poverty of the stimulus. And the poverty of the stimulus. Anybody want to develop that idea for us? It's somewhat similar. What do we mean by the... Okay, Tony's got something.
The information that is on our retina is not all of it is properly translated, and so we lose some of the information. The 2D image that we have underrepresents the 3D.
Yeah. Okay, right. So it's the same kind of an idea, right? The stimulus is said to be impoverished. That is, it underspecifies what's actually out there in the world. And this is an interesting idea that a given retinal image, so I'm looking at that clock, for example, right? A given image of that clock now formed on my retina, that clock can be any of a number of clocks. It can be a clock that's about 20 feet away from me, but it can be a clock that is actually, 40 feet away from me, but twice as big, right? So now it would have the same image on my retina. It could be half the distance. It could be now just 10 feet away from me, but it would be half the size, right? Excuse me, twice the size, rather. So the notion is that we have lots of different clocks that could potentially generate that particular image on my retina, and yet there's only one real clock out there, right? So it's this many to one problem, right? There could be infinitely many clocks because space is infinite, right? We can size it up as it's moving back, we can scale it down as it's moving toward me, but there's only one clock there, and any given retinal image is relatively impoverished, right? It doesn't tell me which one of the many, many clocks could that be. This again, by the way, harkens back to a Gibsonian idea that as I begin to move, I'll get some information about how fast that's expanding or how fast it's contracting, and we'll be talking about a cue called motion parallax in the not too distant future. I guess on Friday we'll get into that. There was some idea about looming in Dr. Jessica Witt's presentation. We get lots of information when we move around that begins to disambiguate which particular clock out of the infinitude of clocks that one is. But for the moment, at any given viewing point, that stimulus is underspecified. It's an impoverished stimulus. It doesn't give us the rest of that information. Yes, please.
So is the problem of the poverty of the stimulus kind of similar to the fundamental problem?
Yeah. And so the idea is that in many, many aspects of perception, we have an impoverished stimulus. One particular case happens to be depth perception. Okay, right? So that's a special case of this. So I wanted to put those two next to each other because as we begin talking about sound, for example, in the next week or two, you'll see that the poverty of the stimulus raises its head again. There will be auditory stimuli that could have come from any number of possible points out here in the real world, but it's really coming from only one. How do we begin to disambiguate that, right? So depth perception is this problem of going from a 3D world to a 2D stimulus is one specific case of the more general problem in psychology of the poverty of the stimulus. Okay, so we'll come back to that a couple of times. Okay, so that was one big idea. Why don't we now have some fun and see if we can get this going? People probably have done some prefusing in different forms. We maybe didn't know it was called prefusing. Before we start, we'll just make sure everybody has their equipment. Your equipment is an index card. And why don't we do this one first? We'll start out with the less interesting geometric shapes, and then we'll move up to something that's a little bit more ecologically friendly.
Thank you.
Okay, so there's that. Okay, and we'll start on the geometric shape side. So we have a different image on the back of this page. Okay, and you probably got a feel for this when you were watching the video, but I'll put this up now on PowerPoint so we can all do this together. Let's go down to right about here. We'll make that really, really big. And we're going to use this as what we might call a septum. Okay? And you can start it here if you like. It works better if you hold it the long way. And then maybe you can lean on over. Why don't we do the top image first? Place this thing in between the left and right panels so that the left side is projecting only to your left eye, the right side is projecting only to your right eye, and then come down right on it. Okay? You can put your nose, your forehead right on that thing, and give yourself a couple of minutes. This actually is a motor skill that I'd like to develop today and also on Friday. And then after you've done it for a few minutes on 2 separate days, if you've gotten some REM in between, we may have trained your brain to do some free fusing. Okay? It also might be the case that you can also, if it helps a little bit, you can lift your card off of the page just a little bit, if that helps you slide things together. You know, so if you need to back off a little, yeah, some people find it a little bit intense, right, because you're really moving your eye muscles quite a bit there. But you can move the page a little bit away from your septum. The idea of the septum is we want the left image to stimulate only the left eye, and the right image to stimulate only the right eye. So we're doing the top one. I'll do it with you. We'll give yourselves a couple of minutes. If you get this trick down, by the way, you'll see that throughout this course, but also throughout your lives, you will have opportunities to free fuse. That's what we're doing right now, to slide 2 images together. And you get some really interesting effects. So we'll stay with the top one, and we'll see, if you're free fusing, don't raise your hand just now, but if you've given it a go and you've got those 2 to slide together, how many people were able to do that? You got, oh, wow, okay, so far, some people are still working on it. That's okay, take your time. We want you to get this motor skill down, okay? For those of you who were able to get it to slide together, can you tell me what it is you saw? I don't want to lead the witness here. We'll see if we get a clear, go ahead, Ann.
I just saw the images converge.
Okay.
But they were kind of blurry.
Okay, yeah, I can see that. They might be a little bit blurry. Farrah, what did you get?
It looked like the oval was up more than the background.
Okay, love what she just did with her hands. Not everybody saw that, but her voice and her hands were just perfect. That the oval in the center was up a little bit and everything else was back a little bit. Why don't we give you a moment to see if you can do that? That will not happen until they slide together. And Abby is correct that it might look a little bit blurry. And it's kind of hard to make that stationary, but we'll give you a few minutes on this motor skill. If you don't get it right away, you shouldn't feel bad about that. By the way, about 5% of the population is stereo blind. We're engaged in stereopsis, a particular kind of form perception that is specific to combining the information from the 2 eyes. Many people who are stereo blind don't know that they are stereo blind until they take an S&P course and everybody else is free fusing and they're all, oh yeah, I see that thing pop out. No, they don't get it. I do have a stereo tester, although maybe many of you have already been tested for stereo blindness. Madison had a question, I think.
Is there a certain side, when I look at it, I see the right eye, and the actual text says right eye. Should you see left or right? Is there...
Yeah, so it's not so much that you should see left or right. Interestingly, that will create a phenomenon called rivalry. We really want you to focus on the geometric shapes, right? So you forget the word left eye and right eye. See if you can focus on the geometric shapes. And by a show of hands, how many people are able to get the central oval to pop up? Does that work for us? Yeah, you can get that to pop up? Okay, pretty cool. Pretty cool that I think that happens. Can we take a moment, and why don't we do the one on the bottom? I'll try not to lead the witness. We'll do now same idea for the one on the bottom. Let your eyes relax. You kind of have to let, almost as if you're focusing a little bit beyond the paper. That tends to slide them together really well. And we'll see how the depth might be different in this image. I'll give you a moment to work on that one. Yeah. And by the way, that's a lot of work for your eyes. And one of the ways to make it a little less intense for your eyes is if you can come up a little bit. Your eyes don't, the further up you are, the less your eyes have to go like this, okay, right? But if you come up too far, then the left and right images both land in one eye, right? In the left eye, both land in the right eye. Okay. This one's, I think, a little harder to see the depth in it, but there is a binocular disparity going on there. See if anybody if you think you can see some depth there, we'll have you raise your hand. This bottom image. Okay, a few folks have it. Tony, do you want to share with us what you think you're getting?
It kind of looks like one image is like on top together.
Okay. And are you getting some depth or not really?
Yeah.
Okay, and what's it?
Further back.
Which one's further back?
Well, it looks kind of like the images are like coming together, but the right one's like coming forward.
Okay, I think that's it. Sarah, is that what you're getting? What is in which depth plane for you when you're looking at this?
It kind of looks like the horizontal line is in the back.
Okay, is anybody else getting that? Horizontal line is in the back? Okay, all right, real good. We'll come back to why that might be the case. That's what's supposed to be happening. We'll see if that's what people are getting. Just for fun, why don't we flip this one over? And now we can just play around with some different orientations. So you should see a circle, and you have a left circle and a right circle. You can place your septum in between those two, and let them slide together. And if it helps you, you can move your paper a little further away from your nose, or just increase that distance a little bit, so your eyes don't have to work, your eye muscles don't have to converge so severely. Did you get that? Anybody get that? This one's a little harder to describe too, but hopefully those circles will eventually perfectly superimpose, and when they do, you get some 3D effect coming out of those two different lines, the shorter line and the longer line, right? They look like they're coming in or out at you, right? So what's really cool is you can tell this is flat as a piece of paper, right? Okay, but when you slide these things together, your brain creates some three-dimensionality, right? So what we're trying to show you here is this is kind of like your left and right retinal image, right? And they are flat as a pancake, right? But if they're in the right arrangement, then your brain can recover some three-dimensionality somehow. It can pick up cues that allow three dimensions to be experienced. Right, okay? All right. How many people got some depth sensation from those circles? Did that work? Not really? Okay, that might be too hard. Okay, why don't we do this? Before we go to the next page, can somebody describe to us, just in words, the Geek trick? How does the Geek trick work for photography? We'll go again with Abby and then with Sarah.
You take like one picture just like straight on something, and then you take another picture that's like 5 centimeters away from it.
Yeah.
And then you like put them on top of each other and like sort of each other.
Yeah, right. it is important when you do that, when I'll click you here, and then I'll go over to this side. Click. You have to remember which one was which. If you get the pictures in the wrong order, you won't get three-dimensionality. They have to be in the same sequence. Was that what you were going to say, Sarah? Okay, and a few folks had their hand up, so thank you. Yeah, that's the idea. So this is, I don't know if that's exactly the same clock, but we were at this point in the semester in 2009. This is my 2009 S&P class. Okay. If I weren't using my iPad right now, I'd take another picture of us. Maybe we'll take a picture of us on Friday. So these are two different pictures. And why don't you give it a go? You can use your card to fit in the center here. Remember to pull back a little bit if it helps your eyes. See if you can get them to fuse, get those clocks to line up right on each other. That is Joe Freundlich, who is one of our S&P students, and he was some kind of an athlete. And a day or two before this session on binocular vision, he sprained an ankle and he was on crutches, and he's sticking his crutch out at us to give us some three-dimensionality. And again, it might help to pull away a little bit from the page, right, so that your eyes don't have to work so hard. After doing this for a few minutes today and a few minutes on Friday, there will come a point where you will be able to free fuse without using this thing. You can just kind of let your eyes relax, and two images will slide together, and you'll be able to see three-dimensionality. Did anybody get it? Sorry, smiling.
I don't think it doesn't work for me.
Yeah, okay. Were you able to get the other ones or not? Okay, all right. If you want, I don't know if you've ever been tested for three-dimensionality. We could give you a test if you're interested in it. It also just might be that there's a challenge in getting our versions done. It's a bit of a motor skill. So we'll see how. Did you ever use the Magic Eye books? Have you ever seen those? They're called Magic Eye, and they're these multi-patterns. You stare at them, and all of a sudden, while you're staring at them, something pops out in 3D. Have you ever seen these things? No? Yeah. They were popular about 15, 20 years ago, but they're not quite as popular as they used to be. They won't go all the way? Okay, so you need to move back a little further. Right? Yeah, right. We'll give you another minute to try these. And don't be afraid to move your head back a bit. You can also bring the septum up with you. Right? That might help. If you bring the septum up with you. That's a pretty good challenge, though. Right? There's a lot of detail in that picture that has to be merged, left eye with right eye. Yeah.
And the longer I look at it, the worse.
So what we're doing here is we're doing free fusing by uncrossing our eyes. Right? Normally we would be crossed this far. We're going to look a little bit past our target like that. We're going to uncross our eyes. You can also do the same thing by crossing your eyes. And there's so-called crossed free fusion and uncrossed free fusion. When you're working with this kind of a septum, we're typically engaged in uncrossed free fusing. Okay, all right, so let's see if we can now get back to some of these other ideas. By the way, I do this all the time when I'm on vacation. I always take two of everything, and then I see my vacation in 3D. It's really a lot of fun once you get that motor skill down. Okay, let's go back to this one just for a moment, and let's look at the top one. And on the top one, we said that the oval was popping out. Can somebody begin to explain why that was popping out and not going backwards? So maybe you can take a look at this image. Okay, maybe Gabby's got it.
So on the left box, the distance between the little circle and the big oval is bigger than the distance between the other one and the other.
Okay, yeah, so we've moved the left-right position of that central circle in such a way that we've created what we will call, in just a moment, a crossed disparity, and we'll see if we can unpack that. So we'll get into the different kinds of disparities. In fact, why don't we go there now? Okay. All right, so first I wonder if we can have somebody begin to explain to us the idea of a horopter. That was a new term for most of us. Zach's got something.
So it's the plane of zero disparity.
Okay.
So,
Yeah, the plane of zero disparity is a good way of thinking about it. It's also the same as our point of fixation. Okay, so right now I'm looking back at Jess. Now I'm going to move my eye a little bit forward. I'm looking at Sarah. Then I'm going to move over to something very close to me. I'm going to look at my own copy of my 2009 S&P class. I'm going to look back at the clock. Every time I move my eyes, I have a new fixation point. And wherever you're fixating, that plane in the z-plane, the plane of fixation, is the horopter. Okay, and that's going to change every time we move our eyes. But for any given fixation, okay, I can be looking right now at Abby, and it would be the case that Madison's going to be further than her, Sarah's going to be closer, and so for that particular fixation, we can say that certain points are further or nearer, right? But there's going to be one plane that we're going to say is our starting point. We'll call that the horopter, and that's the plane of zero disparity. And let's see if we can understand what we mean by that. There's a couple of helpful pictures. So here are two cartoons of eyes. Right? We'll call this your left eye. We'll call this your right eye. And right now they're just looking straight out. Okay. Hopefully people can see that we have A and A prime, B and B prime, F and F prime. And the notion is that A and A prime are corresponding retinal points. Okay. So if a stimulus were to land here, and that same stimulus were to land over here, there would be no retinal disparity, right? On our retinas, they're landing at the exact same locations, A or A prime. If another stimulus landed here and here, they would be projecting to corresponding retinal points. We would not have any difference. But imagine just for the moment that a given stimulus out here happens to be landing on B prime in this eye and A in that eye. Then there would be non-corresponding retinal points. There would be a difference or a disparity. There would be a non-zero disparity. Who's following that? Is that working for us? So are they the same or are they different? And when they're different, we call that a disparity. And they can be different in lots of ways by lots of different magnitudes or by amounts. There can be big disparities, or there can be smaller disparities. For any given point of fixation, right now I'm fixating that computer monitor. As I'm fixating that monitor and things in that depth plane are landing on corresponding retinal points. I'll now move my fixation to look out the window. Okay, now everything at the window's picture plane is going to be at zero disparity or my horopter. All right. People okay with that? If we get the horopter down, we've got an anchor in on this thing. Is there a question on that? Yes.
Just a silly one. Is A, B, and F prime, is it always on the right side of the eye? Is that like...
No, these are just arbitrarily labeled. So we're just saying that we could have picked any point, and we just said that this point corresponds to that point, right? And we're going to call them A, B, and F prime. Sometimes they use F for fixation. Sometimes they use the letter P for fixation point. Okay, but the idea is that you can always sort of rotate these eyes around and then slide them one on top of another, and we can see whether we have the points lining up or not. Okay. All right. So here's another example of the horopter. This person is looking out. Okay, and there's interestingly a bit of a bend. It gets to be very, very complicated. We won't get into all the complications. There are actually multiple horopters. There are different conceptions of horopters with different geometric properties. But to a first approximation, Susan is projecting to G, and she's projecting to G prime. Okay, Ralph is going to F and F prime. Harry is going to A and A prime. They're all on corresponding retinal points. If I slid this retina on top of that one, everything would line up. We'd be at zero disparity. If, though, it were the case that we had Claudio come over here and stand here in the diagram, okay, he's going to land on he's going to generate images in the two eyes that are landing on non-corresponding points, okay, until we fixated on Claudio, and then Claudio himself would be represented on the two retinal corresponding points. So it's interesting, a bit of geometry. I will not ask you to compute any geometry here, just maybe get a feel for what's landing where. Okay? All right, here's where it gets a little bit steep. I hope people followed this in the during our time in the video. Okay? Here's the fixation point. It's going to project to P and to P. But now, for that, you can see that we're going to have this stimulus, which we'll call C, project to this side of this retina and that side of that retina. So if we line up now the P's, all of a sudden the C's are not in corresponding retinal positions. They're in non-corresponding retinal positions. They're off the horopter, which would be right here. Okay? So we're going to get some kind of disparity. The same thing is true for the further point. C is close, F is far. At the further point, it's going to land on non-corresponding retinal points. Who just sees that intuitively? Is that much working for us? Okay? All right, really good. Okay, so then we have basically two flavors of retinal disparities. Okay? Here's the zero plane. Okay? We can have crossed and uncrossed disparities. I wonder if somebody can help us out with that terminology. What do we mean by crossed and uncrossed disparities? Meg's got something.
mostly out of that we actually end up crossing.
Yeah, right. So we wind up crossing our eyes to see something closer, right? Okay, so this point, C, is going to generate non-corresponding retinal images, and it's also going to generate what we would call a cross disparity. In order to get from here to here, we'd have to cross our eyes a little further. Right now, my eyes are like that. If I want to see C, I need to go like that. If I go back up to P and out to F, I'm either uncrossing or crossing my eyes to get from a given point to a further or nearer point. Just following that. Is that working for us? Okay. And every time we change our point of fixation, now we get a whole new set of what is corresponding and what is non-corresponding. But that information, interestingly enough, cells in your primary visual cortex can exploit that information and pull out the third dimension that isn't on either one of your retina alone, right? Okay, it's not, you don't have the depth information here alone, you don't have it here alone, but the combination provides a couple of cues that your brain can exploit. Okay? All right. Okay. So here we are, just to walk through that. I apologize for the very, very light coloring there. Point C generates crossed disparities. Okay, it's closer than fixation. Okay, point F generates uncrossed disparities. It's further away than fixation. Okay, and here we are back at the horopter. Okay. All right, let's see if we can get to a couple of geometric shapes. Why don't we do this? But before we do that, Megan has a question.
Question: with crossing and uncrossing, does that have any change in depth perception, or is that just how we move our eyes to accommodate what we're looking for?
Yeah, so it actually does have a consequence for depth perception. Let's go back over to here, okay, and make sure that we're all clear on that. So let's say you're fixating at this point P, right, okay? This particular stimulus is going to generate non-corresponding points, okay? If you wanted to move from here to here, you'd have to cross your eyes. If you don't move from here to here, you have non-corresponding points, and the particular pattern of non-correspondence will generate a percept that C looks closer to you, okay? And you get a complementary set of retinal disparities for images that are further away, okay? It's almost as if C, things that are closer, this is kind of interesting, they project a little bit more temporally, and things that are further will project more nasally. Who remembers making that distinction between the temporal retina and the nasal retina? Okay, so nasal is going to be close to the nose, temporal is going to be out this way. So here's the point of fixation. You might see that C is projecting a little bit more temporally out to either side, closer to my ears, and the more distant point is projecting somewhat more nasally. Okay? So that neither one is at zero disparity. They're off of the horopter. Okay, but we can ask, gee, are the points from that image relatively nasal, or are they relatively temporal? Okay. And that information alone is enough for cells in your primary visual cortex to do their thing and say, okay, this thing must be closer than Zach. Okay, Jess must be further than Zach. Okay, so let's go to here. We'll do a couple of these. I think people will get the hang of them. Okay, so this is just like what we were doing a moment ago. We have slightly different geometric shapes here than what we had on the page. But imagine that you had, your big septum right over here, and you're trying to get some kind of depth out of this. What change to the left image, that's this one, would make the circle appear near in depth? Okay, so if we're going to change this, what would we do? We'll see how many people can raise their hand and think this through. We're going to make some change over here. Few folks have it. Okay. Here we go, Sibel. What do you think? Was that was a hand? Yeah. Okay. So what do you think? I'm sorry. Well, if you make it bigger, that's a monocular cue, right? Okay. So that's actually not going to be doing anything for us on retinal disparities. That might work, but it doesn't demonstrate a knowledge about retinal disparities, right? Okay. So somebody else, some other idea about maybe Liz has something.
Wasn't that something to do with the objects being closer together?
Okay, and let's think about what do we mean by closer together. So if I took this one and slid it over to the left, this would be closer to that, right?
Or to the right.
Okay, so I go to the right. Okay, so I take this object and I move it to that side. Okay, so it's closer to this one, but it's further than that one. So the statement that we have to make them closer together, we need to be very careful about what way we specify that. But I think you're onto something. If we grab this one, which is in our left image, and we move it rightward, okay, that's going to give us this crossing that I referred to in the video. I'm going to grab that image in my left eye, and I'm going to move it to the right. I'll begin crossing that, and cross disparities generate near percepts, right? So that would do the trick. That's going to make it look near in depth. How many people followed that? Okay. This, by the way, can be enormously confusing to students. So this is why we do this a few different times. And this is not just you. This is true year after year. It took the human species a long time to figure out how they saw stereoscopic depth. Okay? So this is not an easy idea. But after you do 2 or 3 of them, I think it becomes really quite easy. I'll make it really obvious to some folks. This is the extension of my right eye. This is the extension of my left eye. And I'm looking at these 2 images. If I grab that circle in my left eye's view and I move it to the right, I've got something in the left going to the right. Eventually they would cross if I kept on going, and cross disparities generate near percepts. Who's following that? That work? Okay. Let's see if we now get a simple variation on that. What change to the right image would make the triangle, it's over here, okay, so the right image triangle, appear far in depth? Somebody help us out with that. Okay, when we go, Sora? Okay, move that triangle, not the right, move that triangle to the right. Yeah, okay, that would do the trick. Here's another interesting thing. These were created in PowerPoint. If you ever want to do this in PowerPoint and just put up some simple geometric shapes, what's really cool is if you free fuse them, Sora is exactly right. If you move that to the right, you moved it laterally. Perceptually, it'll be moving away from you, okay? So you've made physically a x-axis change. You moved it along the x-axis to the right, okay? So that's a physical movement. We are psychologists here. Psychologically, it moves away from you. If you click it again one more time over, it moves further away. So the further over to the right you move this, the further away it moves from you in depth. Really cool, right? That there's this trade-off between x-axis changes physically and z-axis perceived changes. Right? Yes, please.
How is that movement to the right different than the circle moving to the right, as far as like crossing the shapes?
Okay, so what would happen here is, that's a very good question. I'll pretend this is the extension of my eye again. This eye is looking over that way. This eye is looking over that way. Okay. If I now grab that triangle and I move it to the right, remember that that triangle is on the right side, and I'm moving it further to the right, so I'm uncrossing my arms. Does that help?
Yeah.
It's sometimes hard to see how we're crossing our eyes, but if we hold our hands out this way, we can see that we're uncrossing or crossing. And whenever we grab something over there and move it that way, we're uncrossing, and that's going to make it look further. If we grab something over here and move it that way to our left, that's uncrossing, and it'll make it look further. Okay? Okay, so I think everybody's just about got it, but we always make sure we always end on this one. At least we end this exercise on this one. Okay? And why don't we see what we can do here. Describe 2 different ways of making the cross, okay, I didn't say which one, appear near in depth. Okay, so Sarah's got this one.
So in the left side, you could move it to the right.
Okay, so Sarah told me to grab this one and move it to the right. She's crossing my hands, and that would get a cross disparity, which is near. Or
the right one, you can move to the left.
All right, there we go. Right, all right, so just like that. Right, so you can see how to manipulate these images pretty quickly. Some simple left-right shifts, and that's going to be enough, when free fused, to generate the illusion of depth psychologically. Pretty cool. I love that our brains can do this. By the way, that works, these left-right shifts, because our eyes are laterally displaced. You could at least imagine a species that has 2 eyes, just like you, but they're this way. Okay, right? Then, the left-right shifts wouldn't really buy you anything. But for that animal, presumably, if you had up-down shifts, they would be able to recover some kind of 3-dimensionality from that. But because most animals have laterally displaced eyes, like we do, it's the left-right shifts that matter, and horizontal and vertical shifts really don't have much of an effect. There are some people who do study vertical disparities, but those effect sizes are very, very small. We're not really set up to make vertical disparity judgments. Okay, any questions on that? Who's heard of the movie called Martian? Or The Martian? Yeah, I don't know how long it's been out, but I went to see it this weekend. My wife doesn't usually like to go to movies, but she was raving about this one because she heard so much about it. So what I thought we'd do in our last few minutes is go to planet Mars and look at some pictures from there, but we'll look at them in 3D. So I do have red-blue glasses. You just spent a lot of time pre-fusing using this. We can do it a simpler way using this if our images are color-coded. So I'm going to call up that and ask if somebody would just get these going around. Okay? And I'll call up some images that have been taken from the surface of Mars, and they had one of the rovers do the geek trick. I think it might have been Abby who described that we take a picture here, we take a picture here. NASA arranged to have this Mars rover have 2 cameras, one on the left, one on the right. They put a blue filter in front of one camera. They put a red filter in front of the other camera. They take their picture. They transmit that back using radio waves. Somebody in Houston grabs it, puts it on the web, and it winds up in our S&P class. Okay, so this is truly from the surface of Mars. And this was taken, unbelievably, a little bit more than 11 years ago. Okay, and let's make sure we're in the correct orientation. If you can find your red filter, that's your long wave pass filter, and put it on your right-hand side. You might need to spin your glasses around. So red on left eye. I think that works, red on left eye. And the cyan-colored filter will be on your right eye. Okay, and we'll see. Okay, and this thing is timed. It will take a moment or two for the three-dimensionality to get to you, right? But you are now seeing the surface of Mars. This is not an artist's recreation. This is actually the surface of Mars in 3 dimensions. Okay, even though the screen is 2-dimensional, we're creating retinal disparities through the red and blue. By the way, the movie was fantastic. I highly recommend it. And I just got lucky that it was the weekend preceding our Mars demo for 3-dimensional. You can see the rover's wheels here as it's taking these photographs. Okay? This is the other rover. There were 2, and they were on opposite sides of the planet Mars. How many people are getting some 3-dimensionality? Okay, we'll let the whole thing roll through. So few people in the history of humanity have been able to see the surface of another planet. Arguably, they could with the naked eye. They wouldn't have this kind of resolution. I think that was the parachute that this thing landed on. Okay, now we're back to the other one. So few people have been able to see this, and now you're seeing at great detail the surface of another planet, and you're seeing it in 3D. Do 3 or 4 more pictures. We're doing okay on time, but there's one more twist on this that I'd like to try. And one of these pictures is a little bit out of whack. I think they may have reversed the images to put the right image in the wrong color or something like that. Okay, let's do it this way. In our last couple of minutes, at your leisure, can you flip your glasses up and back down again so that you can see how this thing is colored out here in the real world? And then, of course, what is cyan colored here is making its way only into one of your eyes, and what is colored red is making its way into only the other eye. So it's kind of like having a septum, but now we're separating this by wavelength rather than by using that septum or that index card that we had a moment ago. And it's cool to flip the thing up and see what it looks like en natural, and then to put those back down. And you might be able to see where you're getting cross disparities, uncrossed disparities. In what cases is the blue to the right of the red or to the left of the red? Okay? So the lateral displacements of the red and blue is what's generating the 3-dimensionality for you. Okay, one more time. How many people are getting 3-dimensionality out of that? Okay, I feel very privileged to live at a time when we can see the surface of another planet in 3 dimensions. Pretty cool. Okay, thank you all for giving that a whirl. We're just about out of time. When we come back on Friday, we'll be talking further about depth perception. We'll be talking about my favorite demo, the Pulfric effect. So there's a TED-Ed out there already. I look forward to that. On your way out, would you please bring back the index card so we can try that again on Friday? And maybe you can make a nice clean pile of your red-blue glasses. Okay? Thanks, everybody. See you Friday.